Good morning, good afternoon, good evening, or good whatever, or whenever you are actually listening to this. Today we're going to start a completely new tack where we learn about a second important class of languages other than the regular languages. This class is the context-free languages. They include all the regular languages and more. The most common description for these languages is a context-free grammar. We'll see the definition of these grammars and the way these grammars define languages, which is through derivations. We're also going to introduce a related notation called Backus-Naur form. The two most important applications of context-free grammars are probably in processing natural languages and computer languages. I'm going to focus on computer languages, where almost every language today has its syntax defined by a context-free grammar in the Backus-Naur notation. Grammars are also essential when designing a parser for the language, that part of the compiler that puts together the tokens of the language into the proper structure. For example, the parser discovers the order in which arithmetic operators are applied in an arithmetic expression and groups statements properly so their execution sequence is as intended by the programmer. A context-free grammar defines a language by a mechanism we will soon learn. Every regular language has a context-free grammar describing it, but there are also languages that can be described by a grammar, but that are not regular. On the other hand, the context-free grammar is still a relatively weak formalism. There are some languages that are simple to describe yet have no context-free grammar. Many of the languages in the context-free class that are outside the regular languages are languages that involve nested structures such as the patterns of left and right parentheses that we call balanced. The central elements of a grammar are variables. These are symbols that generate particular sets of strings. One of these symbols, called the start symbol, will generate the entire language, but we can have many others to help us in that definition. The variables, or rather the sets of strings they generate, are defined recursively in terms of one another. The rules that define the languages of the variables are called productions. Each production has a variable on the left, say A, an arrow, and 0 or more symbols on the right. We'll draw, say, X and Y on the right that serve as the definition. A rule like this says that the concatenation of the languages represented by X and Y is a subset of the language represented by A. A variable may have several productions, and its language is thus defined to be the union of the languages described by the right sides of each of its productions. But remember, all of this may be recursive, so grammars are in fact far more powerful than the regular expressions we can build from unions and concatenations. For our first example, let's consider the language that we showed not to be a regular language, the set of strings with a form of n zeros followed by the same number of ones. Here is a grammar for this language. There are two productions or rules and only one variable s. The first production, this one, is a basis rule. It says that the string 0, 1 is in the language of S. The second, this, is an inductive rule. It says that if W is a string in the language of S, then 0W1 is also in the language. That rule lets us build longer and longer strings, at each step adding 1 0 to the beginning and 1 1 to the end, so we always have the same numbers of zeros and ones with the zeros preceding the ones. Now let's make precise our informal introduction to what context-free grammars look like. The terminals of the grammar are analogous to the input symbols of an automaton. They form the alphabet for the language being defined. The variables, or non-terminals, are something like states of an automaton, but they are more powerful. One variable is called the start symbol. It is the language of this variable that the grammar defines. Any other variables are used as auxiliaries, but we can think of them as internal to the grammar, and their languages are not visible outside. The productions of the grammar, which are akin to the transition function of an automaton, have the form of a variable on the left, sometimes called the head, an arrow, and a string of 0 or more symbols which can be terminals or variables. These are sometimes called the body of the production. We have a convention about the letters used for certain symbols and strings. These conventions are more complex than the convention we use to distinguish input symbols, little a, little b, and so on, from strings, w, x, and so on. But they're really important as a reminder of the roles different components play, and it is something worth committing to memory early on. First, we use capital letters at the beginning of the alphabet as variables. However, S is also normally a variable. In fact, it will be the start symbol in many grammars. On the other hand, lowercase letters at the beginning of the alphabet are terminals. This convention agrees with our earlier convention that made these letters stand for input symbols, since there is a good analogy between the input symbols of an automaton and the terminals of a grammar. Capital letters near the end of the alphabet are used for symbols that could be either terminals or variables. We typically don't know which. Lowercase letters at the end of the alphabet stand for strings of terminals only. Again, this matches our earlier convention. And we use Greek letters at the beginning of the Greek alphabet for strings that may consist of both terminals and variables mixed. We'll design a grammar for the language of strings with the form 0 to the n, 1 to the n. The terminal alphabet is 0 and 1, of course. We need only one variable in this case. We'll call it S. S will be the start symbol. There's no other option since it is the only variable. And here are the productions which we explained earlier in our informal discussion. The first production generates only the string 0, 1, and the second production puts a 0 and 1 at the beginning and end, respectively, of a shorter string in the language. A derivation consists of a sequence of strings that typically have both terminals and variables, although they could have only one kind of symbol or even be empty. We start with the string consisting of just the start symbol. At each step, we find a variable to replace, say A. The productions for A, or the A productions, are those that have A on the left side, that is, the head of the production. We replace this A by the right side or body of the production. We can then repeat the process as many times as we like until we are left with only terminals, at which point no replacement is possible, and we have in fact generated a string that is in the language of the grammar. Here's what the replacement looks like. You take any string that has an occurrence of some variable A, and anything to the left and right, terminals and or variables, which is what the alpha and beta we have here suggest. You take an A production whose body is gamma, and you replace the A by gamma. Here is an example derivation. We always start with a string that has just the start symbol S. We choose the second production, so S is replaced by 0S1. Now we replace the S again using the second production, and again we replace the S, but this time we use the first production whose body is just 0 or 1. We are now left with a string that has only terminals, and this string cannot be subjected to further replacements. You should be aware that in more complicated grammars, variables can be replaced by strings that contain 2 or more variables, and when that happens we have lots of choices of what variable to replace at each step, and derivations can be much more complicated. The double arrow symbol represents single steps of a derivation, and just as we extended delta to many steps for automata, we need to have a notation that means any number of steps for a derivation. This is the arrow star symbol, and we define it inductively. Okay. The basis is that in 0 steps the string can't change, so any string goes to star itself. The inductive step lets us get from alpha to beta using any number of steps, including 0 steps. That's that. And then, with one more step, get from beta to gamma. The conclusion is, then, that alpha goes on some number of steps to gamma. Here's an example using the same grammar as before and the same derivation sequence we just discussed. We can conclude that S goes to itself in 0 steps. That is, we just start here, don't go anywhere. So we can conclude that S goes to star itself. Then inductively, S goes to 0, 0S1, rather, 0, 0S1, and 0, 0, 0, 1, 1, 1. Notice also that we don't have to start with the start symbol. It is also true, for example, that 0S1 goes to star 0, 0, 0, 1, 1, 1. Okay. That is, anything along the derivation sequence goes to any later, goes to itself and any later position along the sequence. A sentential form for a grammar is any string derivable from the start symbol. That is S arrow star the sentential form. The sentential form can consist of any mix of terminals and non-terminals. The language of a grammar G is the set of terminal strings W such that the start symbol of G derives W. Here's an example grammar that is just a little different from the previous one. Here the basis rule is that S goes to epsilon rather than S goes to 0, 1. Note that epsilon is a perfectly legitimate body for production, and its effect is to make the variable on the left disappear. As a result, this grammar can derive the empty string along with all the other strings that have some number of zeros followed by the same number of ones. That is, the language of this grammar is the set of 0 to the n, 1 to the n, such that n is at least 0, while the previous grammar had at least 1 as the condition on n. The class of languages called context-free languages consists of all those languages that are defined by some context-free grammar. We now see that there are context-free languages that are not regular languages, such as the 0 to the n, 1 to the n example just given. However, there are languages that are not context-free, and the intuition is that context-free grammars can count 2 things, but not 3. Thus, an example of a language that is not context-free is 0 to the n, 1 to the n, 2 to the n, say such that n is equal to or greater than 1. That is, you cannot match both the zeros against the ones and the ones against the 2 at the same time. I want to introduce a notation called BNF, or Backus-Naur form, which you may have seen in manuals for programming languages, and which is closely related to context-free grammars. BNF has a number of extensions to the grammar notation we use, and these extensions are useful in manuals but don't add any power. BNF-style notations were used for 2 of the original programming languages. John Backus used it in the original description of Fortran, and Peter Naur used it in the original description of Algol. In BNF, you usually use a word to describe a variable, for example, statement, if the intent is that this variable will generate all the strings that are valid statements of the programming language. Conventionally, these words are put in triangular brackets to tell us they are variables rather than terminals. Some terminals for a programming language are single characters, just like in our formal context-free grammars. For example, the plus sign or semicolon are commonly terminals in the grammar for a programming language. However, other terminals are really reserved words like if or while. And we see these shown either in bold or underlined depending on the style used to remind us that they are single symbols. In BNF we often find colon equals used in productions rather than the arrow. We also find a vertical bar used to list several production bodies that have the same head. That is a useful convention that we shall use in formal grammars as well. For example, our original grammar can be written with S once on the left side and the bodies of the two S productions listed with the bar connecting them. Another extension of BNF is similar to the Kleene star, but it means one or more rather than zero or more. We follow a symbol or a bracketed expression by ... to mean one or more occurrences of the symbol or the symbols within the brackets. So here is an example. We have one variable, digit, with the obvious 10 productions, all grouped together with the bars. Then we have one production for the variable unsigned integer with right side digit ... that is one or more digits. In general, we can replace alpha ... by two productions. Let A be a new variable that generates all sequences of one or more alphas. A has two productions with bodies A alpha and just alpha. You should be able to see how A can be replaced by any sequence of n alphas. Just use the first production n-1 times and the second production once. For example, here is a grammar for unsigned integers where the BNF d ... has been replaced by these two productions. These generate any sequence of one or more d's. Then d generates each of the 10 strings consisting of a single digit. That's, of course, that. We can make part of a production body be optional if we surround it by square brackets. For example, many programming languages have both an if-then and an if-then-else construct for statements. We can see this as an if-then statement with an optional else clause. In BNF, we put brackets around the else clause to make it optional. That's essentially this stuff there. We can replace an optional alpha by a new variable A. This variable has two productions, one with the body alpha and the other with the empty string for a body. Thus, the alpha can be either there or not when we expand the new variable A. Here we're using I for if, T for then, and E for else, and the semicolon is another terminal standing for itself. S is the start symbol standing for statement, and C is another variable representing conditions. We really need to add productions for conditions, but I haven't done so in this fragment of a real grammar. Notice that A is a variable standing for an optional else clause. It can be replaced by a semicolon, an else, and another statement if we want to have the else clause there, or by epsilon if we just want an if-then statement with no else clause. Curly braces are used in BNF for grouping several different elements. You need this, for example, if you want to have a repeating group of elements in a ... or one or more construct. For example, it is common in programming languages to allow a statement list to be one or more statements. The statements are separated by semicolons, so there is one fewer semicolon than statements. That is, a statement list consists of one statement, that's this, followed optionally by one or more groups consisting of a semicolon and a statement. There. Brackets form a group, and then finally the ... applying to the group says one or more of these groups. Finally, you have the braces, and those braces say that the whole thing is optional. To translate groups to our original notation, just create a new variable A for the group. A has one production whose body is the group. Here's an example of a production that uses all three BNF features, one or more, optional, and grouping. It says a list of statements L is a single statement S, optionally followed by one or more groups, each group consisting of a semicolon and a statement. The first thing we'll do is replace the group semicolon S by a new variable A. A has one production in which it is replaced by the thing it stands for. That's this guy right here. And next, we'll introduce a new variable B, which stands for the optional A dot dot dot. B has two productions. It is replaced either by the A dot dot dot, that would be this choice, or it is replaced by the empty string. Finally, we replace the A dot 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 in the B productions by the new variable C. The productions for C, which are here, allow C to be replaced by any sequence of one or more A's. When a sentential form has a number of variables, we can replace any one of them at any step. But what string of terminals a variable ultimately gets replaced by is independent of what else is in the sentential form. That's actually where the term context-free comes from. As a result, we have many different derivations of the same string of terminals. We can restore some order to the world by requiring that a particular variable be replaced at each step, although we cannot demand that any particular production be used for the replacement. One reasonable rule is to require that the leftmost variable be the one replaced at each step. This rule restricts us to what are called leftmost derivations. Similarly, we could require that the rightmost variable be replaced at each step, and that gives us the rightmost derivations. The double arrow with an LM subscript, that's this, represents one step of a leftmost derivation. That is, on the left of the arrow LM, we must have a string of the form WA alpha. Here you see one. That is, since W by our convention has terminals only, A must be the leftmost variable in the string. On the right is the same string with the body, say beta, that, of some A production replacing A. The symbol consisting of the double arrow with a subscript LM and a star, that's this, means becomes by a sequence of 0 or more leftmost derivation steps. Let's introduce another very simple grammar that generates a language that is not a regular language. This grammar has only one variable, but unlike the 0 to the n, 1 to the n grammar, there are productions with more than one variable in the body. This grammar generates strings of balanced parentheses, those strings that are legal in arithmetic expressions. The last production, here's its body, says that a pair of matching parentheses is balanced. Of course, the left parenthesis must come first. The middle production, this, says that if we put matching parentheses around a balanced string, it is still balanced. And the first production, this, says that the concatenation of two balanced strings is balanced. We need to prove that every string of balanced parentheses can be generated by this grammar. The proof is not too hard, but we're not going to do it here. Here's an example of a leftmost derivation. We start with just S, so that is the leftmost variable. Okay. We replace it by two S's at the first step. There we go. Next, the first of these S's must be replaced in a leftmost derivation. We choose the second production for the replacement. There we are. At the third step, the first of the S's must be replaced, and here we choose the last production in the replacement. That's giving us that. Okay. At the last step, we have only one S, and that naturally is the one we replace. We have chosen to replace it using the last of the three productions, so now we have a terminal string and are done. The arrow star leftmost notation can be used to express 0 or more leftmost derivation steps. So, for example, S is related to the terminal string by this relationship. It is also related to itself and all the other steps in the derivation by the same relationship. And in fact, each step is related to itself and all the following steps. Okay. Here is an example of a derivation that is not leftmost. The problem is that at the second step, the second s, rather than the first, was replaced. Rightmost derivations are defined quite analogously to leftmost derivations. The arrow with an rm subscript, this, means that the rightmost variable was replaced at the step. Notice that the string on the left, which is this, has w, which must be a string of only terminals following the variable a that gets replaced. Thus a is surely the rightmost variable. And the arrow with a rm and a star means 0 or more steps of a rightmost derivation. Okay. Here's our balanced parenthesis grammar again. Now we have a rightmost derivation of the same string as before. Notice that at the second step, the second s got replaced rather than the first. S is related to the terminal string by the arrow star rightmost operator, and as for leftmost derivations, each step in the rightmost derivation is related by this operator to itself and all the steps that follow. Here's an example of a derivation that is neither leftmost nor rightmost. See how at the third step, the middle s is replaced. Also, notice that the second step is correct, but ambiguous in a concerning way. One of the s's here, one of these two, got replaced by two s's, but we don't know which. The parse tree is a graph that shows how a particular string was derived using some context-free grammar. These trees have a direct connection to leftmost and rightmost derivations, which we shall explain now. One important use of the tree representation of derivations is that it lets us express the important concept of ambiguity in grammars. That is, unambiguity, or the ability of a grammar to provide a unique tree structure for every string in its language, is vital. For example, if a programming language has ambiguity, then there are programs with two or more distinct meanings. The same is true of a grammar for a natural language. It would be insufficient to provide an intended meaning for all valid sentences of the language. Parse trees for a grammar G are trees whose nodes are each associated with a symbol of G. I'm going to draw you a little tree here. Leaves are always labeled by either a terminal or by epsilon. So we might draw, for example, an A on that one, a terminal B on that one, and perhaps epsilon on that. Interior nodes are labeled by a variable. Here are some examples. The important property that makes a tree a parse tree is that there is a production of the grammar with the label of the node in question as its head and the labels of its children read left to right as its body. Okay. For example, if you look at this parse tree, we would infer that A goes to BC is a production. Also, B goes to little a, little b is a production, and C goes to epsilon is a production. The root must be labeled by the start symbol. In our example tree here, I'm going to have to guess that if this is the root, then A is in fact the start symbol. Here's a parse tree using the grammar for balanced parentheses that we discussed earlier. Notice how each interior node is labeled by a variable. It's here, 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 and here. It must be S because that's the only variable we have. Okay, each leaf is labeled by a terminal, either a left or right parentheses. These are here, 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 and here. Okay, the production at the root is S goes to SS. You can sort of see that by looking at the root and its two children. Okay. Here's another interior node, and the labels of its children are left paren, S, right paren, and you know that left paren, S, right paren is another production of the grammar. That's right here. And here we have an example of an interior node labeled S, and its children are labeled left paren, right paren. That corresponds to this production body right here. You have the same exact use of that production here. Okay. The yield of a parse tree is the string of labels of the leaves from the left. This order of leaves is the order you visit them in during a pre-order traversal. The path would look something like this. That's sort of a pre-order traversal path, goes around the tree counterclockwise. The order in which you visit the leaves is the order in which their labels appear in the yield. So here the yield is left paren, right paren, right paren, left paren, right paren. That's what we said here. In what follows, we're also going to talk about parse trees with a root A that might not be the start symbol. These trees follow all the other requirements of a parse tree. The leaves are labeled by terminals or epsilon, and an interior node with its children form a production of the grammar. We're going to show how to convert parse trees to leftmost or rightmost derivations and vice versa. As is often the case, our road is made easier by proving something more general than what we really need. In this case, we'll talk about generalized parse trees that can have any root label, say A, and we'll talk about leftmost and rightmost derivations from any variable A. We'll prove two statements. One is that if there's a parse tree with root A and the yield W, then there's a leftmost derivation of W from A. The second statement is the converse, that for every leftmost derivation of W from A, there is a generalized parse tree with root A and yield W. The matter of rightmost derivations is completely analogous. We'll start with point 1 by showing how to convert parse trees to leftmost derivations. The proof is an induction on the height of the tree. The basis is height 1. That is, a tree consisting of a root labeled by some variable A and one or more leaves. There must be a production with head A and body being the labels of the leaves from left to right. That's A1 through AN in this picture. Okay. Then A derives the yield of the tree by the one-step leftmost derivation in which this production is used. For the induction, we'll assume statement 1 for height less than h and prove it for h. That is, we assume for every parse tree with root A and height of up to h minus 1, there's a leftmost derivation of its yield from its root. Now let's look at a parse tree of height h. The case h equals 1 is the basis, so h is at least 2. Thus, the production used at the root has at least one variable on its right side. Say this tree has root A and the children of the root labeled x1 through xn. If xi is a variable, then it is the root of some subtree of height at most h minus 1 and some yield, say wi. If xi is a terminal or epsilon, then we imagine xi is the root of a trivial tree, not a parse tree, that consists only of the node labeled xi. Okay. The yield of this tree is just xi itself, but for consistency we shall refer to xi as the string of terminals wi. The yield of the entire tree is w, which is w1 through wn. We can put together a leftmost derivation of w from A as follows. Start by applying the production at the root. So the second step is x1, x2 up to xn. That's this. Okay. Now we need a leftmost derivation of w1 from x1. If x1 is a terminal, then it equals w1, so we're already there. And this step is then really 0 steps. On the other hand, if x1 is a variable, then we apply the inductive hypothesis. The subtree with root x1 and yield w1 has height at most h minus 1, so there is a leftmost derivation of w1 from x1. In that case, this x1 has been replaced in a leftmost derivation by w1, and this goes to star, represents all the steps that were necessary to replace x1 by w1. Either way, we can conclude that there's a leftmost derivation of w1 x2 through xn. That's this. We can continue arguing this way for each xi in turn. Either it is a terminal, in which case nothing needs to be done, or it's a variable, in which case we can perform a leftmost derivation of wi from xi. The needed sequence of leftmost derivations is a leftmost derivation of the entire yield w, that's w1 through wn, from A. Now we need to prove the other direction, that leftmost derivations can be turned into parse trees. The proof is an induction on the number of steps of the derivation. The basis is a one-step derivation. In this derivation, a variable A is replaced by a string of terminals, perhaps the empty string, using some production for A. If the string is not empty, then there's a parse tree of height 1 with A at the root and the sequence of terminals in the body as the labels of the children. It's this, and there are the children. Okay, if the body is epsilon, then there's again a parse tree. It has A at the root and one leaf labeled epsilon, so it just sort of looks like this. Now let's do the inductive step. We assume that leftmost derivations of fewer than k steps can be turned into parse trees with the proper yield, and we'll consider a k-step derivation from string w from variable A. The first step of this derivation uses a production with head A and body x1 through xn for some n. Thus, the second sentential form in this derivation of w is x1 through xn. That's that. Remember the important properties of derivations, that production bodies replace production heads at the position where the head is. Thus, we can divide w into the concatenation of n strings, w1 through wn, in that order, where for all I, wi either is xi if xi is a terminal, or xi derives wi by a leftmost derivation of fewer than k steps. Since the whole derivation is leftmost, the derivation of w1 from x1 must happen first, then the derivation of w2 from x2, and so on. So we know that each xi either is wi or derives wi in fewer than k steps of a leftmost derivation. For the second case, where xi is a variable and the leftmost derivation takes one or more steps, the inductive hypothesis tells us that there is a parse tree with root xi and yield wi. Thus, we can build the parse tree shown, that is this. The root uses the first production of the derivation, that is A goes to x1 through xn, and the ith child either is wi if xi is a terminal, or it is the root of a parse tree from xi deriving wi. The yield of this tree is w1 through wn, which is w. Okay, that is, string w is w1 through wn. All these strings are derived left to right in that order. This proves the inductive step, and we conclude that there is a leftmost derivation of w from A. Then there is a parse tree with root A and a yield w. It is also true that if there is a rightmost derivation of w from A, then there's a parse tree with root A and yield w, and conversely. But we're not going to prove that part. The proofs are essentially the same as what we have seen. And in fact, any derivation, even one that isn't leftmost or rightmost, of a terminal string w from variable A implies that there is a parse tree with root A and yield w. The first step of any derivation from A must use a production and replace A by some string of terminals and variables, say x1 through xn. If w is the terminal string ultimately derived, then we can still break w into w1 through wn, where each wi either is xi or is derived from xi by fewer steps than the whole derivation. The only tricky part is that now the steps of the derivations from xi and xj may be intermingled, and we have to sort the derivation steps according to which xi's descendant is being replaced at that step. We'll leave you to think through the details of this construction of parse trees. As we mentioned at the beginning, it is important in many applications, including parsing of programming languages in a compiler and parsing of natural language sentences, that we use a context-free grammar that assigns a unique parse tree to each string of the language. We say a grammar is ambiguous if there is at least one string in its language that has two different parse trees. Otherwise, it is unambiguous. The grammar for balanced parentheses that we have been using is ambiguous, alas. I'll show you two parse trees for this balanced string, that is left, right, left, right, left, right, on the next slide. Notice that each of these trees has the same yield, that is 3 pairs of left and right parentheses. However, they are evidently not the same tree. The first replaces the first child of the root by SS, and the second does the same but with the second child. Notice that the two constructions we just gave, leftmost derivations from trees and trees from leftmost derivations, have the property that two different parse trees produce different leftmost derivations, and conversely. The same is true for the analogous transformations between rightmost derivations in trees. Thus, we could also define a grammar to be ambiguous if it has a string with two different leftmost derivations or two different rightmost derivations. Fortunately, just because one grammar for a language is ambiguous does not mean that we can't find another grammar for the same language that is unambiguous. But as an aside, which we'll get to later, the opposite is not true either. That is, there are some ambiguous grammars for which no unambiguous equivalent exists. Anyway, here is a grammar for balanced parentheses that is unambiguous. Variable b, which is the start symbol, generates all balanced strings. But r, another variable, generates all strings that are balanced except for having one more right parenthesis than left. By balance in this context, I mean that no prefix of the string has more right parentheses than left. And examples would include, a single right paren, left, right, right, that would be generated by r, and also something like this. Left, left, right, right, right. Here's the unambiguous grammar for balanced parentheses again. Suppose we're given a string of parentheses which we'll call the input, and we want to find its leftmost derivation or derivations. We claim that for every input symbol, and for either variable b or r, there is only one choice of production that could possibly lead to a leftmost derivation of the input. That is, no string of parentheses has two distinct leftmost derivations, and therefore the grammar is unambiguous. Imagine we are constructing the left sentential form as we scan the input. As we go, the terminals to the left of the leftmost variable must match the input, or we'll never derive that input string of terminals. So we can check off input symbols as we match them. Notice that the only place b can ever appear in a left sentential form is at the right end. That is because the only production with b in the body has that b at the right end, and it also has head b. That is, this b can only go to a string that has a b in it, and the only way a b can appear is if it was either the start symbol or it was the result of replacing this b at the end by the paren rb in that production. Thus, an easy induction on the number of times this production is applied shows that the b is still at the right end. Now suppose b is the leftmost variable of a left sentential form. If there's a left parenthesis as the next unmatched input, then we have to expand the b using this production, the paren rb. Because if we use epsilon, then the left sentential form has no more variables, and we can never generate the unmatched left paren. The only time we can use epsilon to replace b, that's this production, is when we have matched the entire input and we have found the unique leftmost derivation. If r is the leftmost variable, then the next input symbol forces us to use one of the two r productions. That is, if the next input symbol is right paren, you must use r goes to right paren. That's here. And if the next input is a left paren, you must use r goes to left paren followed by two rights. There's never an option, or the left sentential form we are deriving can never match the input string. Here's an example. Suppose we want to find the unique leftmost derivation for this string of parentheses. That's this string right here. We set the string up as an input with a pointer to the next symbol that must be matched in the leftmost derivation. Okay. We start off with the left sentential form, that is the start symbol b alone. Okay. The next input to match is a left paren, and we must therefore expand this b to left paren rb, that is, using that production. Here we've made the expansion. The first left paren is removed from the input since it has been matched. That is, it appears to the left of the leftmost variable in the current left sentential form. In essence, this left paren is what used to be on the input there. Okay. Our next input symbol is another left paren, and we have to expand in r, the leftmost variable. That's this guy. Our only choice is to use the body r goes to left paren r. Okay. That's what happened here. The r was replaced by paren r, and the second left paren has been matched. It appears to the left of the leftmost variable, as here. Now the next input is a right paren, and we must expand the leftmost r. The only choice is the first production, that will enable us to match. Now the third input has been matched. We have r to expand, and the right paren as the next input. So we again use r goes to the right paren. That is, we expand that r, replacing it by a right paren. That's what's going to happen on the next slide. Here the left paren is the next input, and we must expand b. The choice is the first production for b. That. Now r is the leftmost variable. We're up here now. And the next input is the right paren. So we replace the r by right paren using the first production for r. That's that. And let's see. Now there's no more input to match, and b must be expanded. That's b, the leftmost variable. The only choice is to use the second b production, which is that, and we effectively make the b disappear. And we're done. We have a leftmost derivation of the original input, which of course appears as the final step of the derivation. Had we deviated from the choices we made at any step, the result of the leftmost derivation would not have been this input string of terminals. There is a name for grammars such as our example, where it is always possible to choose a unique production to use in a leftmost derivation of any string in the language, in the simple manner that we illustrated. At each step, we looked only at the first unmatched symbol of the input, and we were able to make the unique choice correctly. Such a grammar is called LL of 1, standing for leftmost derivation, that's the first L, left to right scan, that's the second L, and one symbol of look ahead. It is normal for a programming language to have an LL of 1 grammar. Probably, as this theory became widely understood by designers of programming languages, they saw the advantages of keeping the language parsable in this simple way and made choices to preserve this ability. And the same argument we gave for our example grammar tells us all LL of 1 grammars are unambiguous. And remember, unambiguity is vital for a programming language, as we must assign a unique meaning to any legal program of the language. For balanced parens, we found the first, simplest grammar that we wrote down was ambiguous, but we were able to redesign the grammar to make it unambiguous. One might hope for an algorithm that would do that for any ambiguous grammar. But alas, there cannot be such an algorithm. There are certain context-free languages for which every grammar is ambiguous. Such languages are called inherently ambiguous. We're not going to get into the proofs of what I just said, but I'll give you an example of an inherently ambiguous language. The set of strings of the form some number of zeros followed by some number of ones followed by some number of twos, such that either the numbers of zeros and ones are the same, that would be this condition, I equals j, or the numbers of ones and twos are the same, that would be j equals k, or both, of course. The problem is that any grammar for this language must generate at least some of the strings with equal numbers of all three symbols in two different ways. In the first derivation, or parse tree, the grammar forces the numbers of zeros and ones to be the same, using the same trick we use to generate a set of strings with the form 0 to the n, 1 to the n. The grammar can generate any number of twos to go along, but it may happen to generate the same number of twos as zeros and ones. The second derivation of parse tree makes sure the numbers of ones and twos are the same, but it may accidentally generate the same number of zeros as well. Here's an example grammar. It is ambiguous, but that doesn't prove the language is inherently ambiguous. As I said, we're not going to give that proof. It's very complicated. However, you might wish to play around with grammars for the same language and see how you are forced to do something like this grammar in order to generate exactly the language we want. It should be easy and familiar to observe that A will generate all strings with one or more zeros followed by exactly the same number of ones. We've seen essentially this pair of productions here as a complete grammar before. And it should also be obvious that B generates any string of one or more twos and nothing else. Likewise, C generates the strings of one or more zeros, and D generates one or more ones followed by exactly the same number of twos. Now, all derivations start with S, and the first production replaces it by either AB or CD. If we go with AB, then we get strings where the zeros and ones match, while if we go with CD, then the ones and twos match. As a result, strings like 0, 1, 2 with the same number of each symbol will have two leftmost derivations, one starting with S goes to AB, that's this, and the other starting with S goes to CD. Here are the two derivations for 0, 1, 2. Context-free grammars can be badly designed. For example, they can have variables that play no role in the derivation of any terminal string and therefore shouldn't be there. That is analogous to states of a finite automaton that aren't reachable from the start state. There are also certain productions that, while they are necessary, cause derivations to take many steps that can obviously be combined. These include productions whose bodies are the empty string, or unit productions where the body is a single variable. We can get rid of these, and the way to do so is similar to the way we removed epsilon transitions from an NFA. Finally, we're going to introduce Chomsky normal form, where all the production bodies are either a single terminal or two variables. Incidentally, the Chomsky referred to is Noam Chomsky. Back in 1956, he wrote the paper that introduced the idea of context-free grammars. Then he was a linguist trying to provide some mathematics for the structure of the language. Since then, he has unfortunately become somewhat notorious for his political views. Oh well, back to context-free grammars. Here is an example of a really bad grammar. A is okay. It derives all strings of one or more A's using its two productions. However, B has only one production, and that production has B in its body. Thus, once a sentential form has a B in it, you can never get rid of that B, and as a result, B derives no terminal strings. To make matters worse, S has only one production, so that must be the first used in any derivation, But that production introduces a b into the sentential form, so it is impossible to derive any terminal string from S, and therefore the language of this grammar is empty. Almost all the algorithms we need to simplify grammars are based on the same principle, which I call discovery algorithms. These discover facts by an induction process. The basis is always certain facts that are obvious. Then, based on what is already known, we discover more facts in repeated rounds. Finally, at some round, they can discover no more facts. There's no point in going on, since without new facts at the current round, we cannot discover more on the next round. We generally have to prove only that any true fact of the type we are trying to discover will be found this way. Here's the image of discovery algorithms we should keep in mind. Okay, we start with some facts that you get from the basis. We expand the set of facts you know by using the basis facts. This is the first round. For the second round, we expand the set of known facts further by using both the basis facts and the facts you discovered at round 1. You keep going until at some round you have no more facts that can be discovered. So one of the first things we need to do when dealing with grammars is to detect and get rid of variables that can't derive any terminal string. We shall give a discovery algorithm to find inductively all variables that do derive at least one terminal string. Any variable not discovered by this algorithm derives no terminal strings and can be eliminated. For the basis, if a variable A has a production whose body has no variables, then A certainly derives a terminal string in one step. Note that this body could be the empty string. Technically, the empty string is a string of terminals. Now, suppose A has a production with a body alpha, and alpha consists only of terminals and variables that we have previously discovered to derive some terminal string. Then we can also conclude that A derives a terminal string. Since the number of variables is finite, eventually this algorithm terminates where it can find no more variables that derive terminal strings. It is easy to prove that whenever the algorithm says a variable derives a terminal string, that it really does derive a terminal string. We're not going to prove that. The harder part is showing that the algorithm doesn't miss anything. That is, if variable A derives some terminal string, then the algorithm will eventually discover A. We'll do that on the next slide. The proof is an induction on the minimum height of a parse tree with root A and a yield of terminals. The basis is a tree of height 1, which consists of root A and one or more leaves labeled by terminals, or perhaps epsilon. Then the basis step of the algorithm discovers A, so we're okay there. For the induction, assume the statement is true for height up to h-1. That is, all variables that are the roots of parse trees with height up to h-1 and a yield of terminals are discovered by the algorithm. The parse tree for A of height h, which must be, of course, equal to or greater than 2, has children of the root labeled x1 through xn. That's this. Any one of these xi's that is a variable is the root of a subtree of height at most h-1, and therefore it is discovered. Moreover, one of these variables is discovered last. At the round where the last of the variable ai's is discovered, we must surely do another round since the set of discovered variables just changed. On the next round, A will be discovered because it has a production, that is, A goes to x1 through xn, whose body consists only of terminals and discovered variables. The algorithm to eliminate variables that derive no terminal string is now simple. Use the algorithm we just described to find the variables that do derive terminal strings. Call the other variables useless. Then remove from the grammar all productions in which at least one useless variable appears. It doesn't matter whether the variable appears in the head, the body, or both. Here's an example grammar to which we first apply the algorithm to discover variables that derive terminal strings. For the basis step, we immediately discover A and C because they have productions with bodies that are terminals only. Here they are. For the first round of the induction, S is discovered because there is an S production with body C, and C was previously discovered. However, at the next round, we can discover no more variables. The only variable we have not yet found to derive a terminal string is B, and B has only one production body, which is little b, followed by big B. But this body does not consist only of terminals and discovered variables, so we can never add B to the set of discovered variables. Thus B is useless and we eliminate all traces of it. That includes not only the production B goes to BB, but the production S goes to AB, leaving us, of course, fortunately, S goes to C, still remains, as well as the two A productions and the C production. In addition to eliminating variables that don't derive anything, we need to eliminate variables that derive some terminal strings but cannot be derived from the start symbol. The algorithm to find symbols, both terminals and variables, that appear in derivations from the start symbol is another example of a discovery algorithm. For the basis, obviously the start symbol can be derived in 0 steps from itself. For the induction, suppose that we have discovered that we can reach variable A. Then for every production with body alpha and head A, we can also reach all the symbols appearing in alpha, the terminals and variables that appear there. It is an easy pair of inductions to show, first, that if we discover a symbol by this algorithm, then it appears in a sentential form derivable from the start symbol. Second, that if we do not discover a symbol, then there is no derivation from the start symbol in which it appears. We're not going to give the proofs here. But remember, our goal is to get rid of symbols that do not appear in the derivations from S. So after discovering all the symbols that do appear in a derivation, delete from the grammar all the productions that contain a symbol in either the head or body or both that does not appear in a derivation. Say a symbol is useful if it appears in a derivation of a terminal string from the start symbol, and call it useless otherwise. There are two reasons a symbol could be useless. Either it derives no terminal string, or it appears in no derivation from the start symbol, or both. We have algorithms to eliminate symbols that are useless for each of these reasons, but we must apply them in the right order. First, eliminate the symbols that fail to derive a terminal string. And then eliminate symbols that do not appear in any derivation from the start symbol. In this example grammar, if, as we should, we first eliminate variables that do not derive a terminal string, we eliminate only B. However, eliminating productions with B gets rid of the only S production. We then use the algorithm to find symbols unreachable from the start symbol, and we find everything is unreachable. That is, all the productions are deleted. However, if we do things in the wrong order and first eliminate unreachable symbols, we find everything is reachable from S, so nothing is eliminated here. Then, when we look for the symbols that do not derive terminal strings, we eliminate only B. That leaves the productions A goes to C and C goes to little c, these guys, which should not be there because A, C, and little c are useless. Here's why first eliminating variables that don't derive terminal strings is the right thing to do. After eliminating those variables, every remaining symbol is either a terminal or it is a variable that derives a terminal string. After removing symbols not reachable from the start symbol, all remaining symbols appear in some derivation from the start symbol of some sentential form. But the variables that appear in sentential form still derive a terminal string because such a derivation can only involve symbols that are also reachable from the start symbol. Epsilon productions are those that have body epsilon. They can be eliminated from a context-free grammar, and the only thing that we lose is that we can no longer derive the empty string. If the empty string was not in the language to begin with, then we can eliminate epsilon productions and still have a grammar that derives the same language. However, if epsilon was in the language, then we lose it. The two cases can be summarized by the theorem on the slide. If L has a grammar, then L minus the set containing the empty string has a grammar with no epsilon productions. Notice that if epsilon was not an L, then L minus epsilon is just L anyway. To eliminate epsilon productions, we need yet another discovery algorithm, this one to find the variables that derive the empty string by one or more steps. We call them nullable symbols. The basis of the discovery algorithm is that if A has a production with an empty body, then it is surely nullable. And the induction is that if A has a production with body alpha, and alpha consists only of variables that are nullable, then A is also nullable. Here's an example grammar for which we will discover the nullable symbols. For the basis, we know A is nullable because of the production with epsilon body. It's that. In the first round of the induction, we find B is nullable because of the production B goes to A. That is, all symbols in the body, namely the A, are already known to be nullable. In the second round of the basis, we discover S is nullable because of its body AB, both symbols of which are already known to be nullable. This algorithm finds all and only the nullable symbols. We're not going to give the proof, which consists of two simple inductions. To eliminate epsilon productions from our grammar, we need to turn each production, say A goes to x1 through xn, into a possibly large number of productions. The idea is to guess which of the nullable symbols in the body of a production will derive epsilon in a particular derivation. Since we make all possible guesses by creating many different productions, we always manage to guess right. More precisely, for each set of nullable xi's, we delete these from the body of the production and make a new A production. Note that if two of the xi's are the same nullable symbol, then we have to consider the possibility that one position derives epsilon and the other does not. That is, we form one production for each set of positions that hold nullable symbols, not just for each set of nullable symbols. However, in the special case that all the xi's are nullable symbols, we do not consider the set of all positions, and we do not create a new production with the epsilon body. Here's an example grammar. Each of A, B, and C are nullable because they have epsilon productions. Okay. Thus, S is also nullable because of its production S goes to A, B, C. Let's construct the new grammar. For the S production, there are 7 subsets of nullable positions that we must use. The set of all 3 positions is also nullable, of course, but eliminating all of A, B, and C would leave an empty body which we don't allow. However, if we use the empty set of positions, we get body A, B, C. If we use the set of only the third position, we get A, B, and so on. Now let's look at the A productions. We do not use A goes to epsilon, of course, but for production A goes to little a, big A, that's that. Only the second position is nullable, so we get 2 productions, one with the variable A present and the other not. That's what we have here. The situation for B is the same. However, for C we cannot use the C goes to epsilon production. So in the new grammar, C has no production. That means that in the new grammar, although not in the old grammar, C is useless and must be eliminated. That forces us to eliminate all productions with C in the body, and we are done. The proof that the new grammar we construct generates the same strings except for epsilon as the old grammar generates is a little tricky, so we're going to give the details in one direction. As is often the case, we need to prove something more general than we really need. In this case, we need 2 statements about every variable A. First, if W is a non-empty string that is derived from A in the old grammar, then A also derives W in the newly constructed grammar. Second, if A derives W in the new grammar, then first of all W is not empty, and second, A derives W in the old grammar. Once we have that for all A, we can apply the statement to the start symbol and thus prove that the language of the new grammar is the language of the old grammar with epsilon removed if it was in that language. We're going to prove the first direction, and it is an induction on the number of steps by which A derives W in the old grammar. For the basis, if there's a one-step derivation of W from A, then A goes to W must be a production. We assume in part 1 that W is not empty, so A goes to W is a production of the new grammar. We make the desired conclusion that A derives W in the new grammar. Now let's do the induction. Assume the inductive hypothesis for derivations of fewer than k steps, and suppose W is derived from A in k steps of the old grammar. The first step of this derivation must be A replaced by the body of some A production. Assume this body consists of symbols x1 through xn. Then we can break W into W1 through Wn, where each Wi is the portion of W that either is xi, if xi is a terminal, or is derived by xi, if xi is a variable. All these derivations from variables are in fewer than k steps. If xi is a variable and the piece Wi is not empty, then the inductive hypothesis tells us that xi derives Wi in the new grammar. When we constructed the new grammar, we replaced the A production A goes to x1 through xn by a family of productions, and one of these eliminates from the body exactly those xi's such that Wi is epsilon. We know that is the case because if Wi is epsilon, then surely xi is nullable. We also know that not all Wi's are epsilon because W is not epsilon. That is, at least one xi is either a terminal or it is a variable that we do not need to remove from the body. Thus, in the new grammar, the first step can replace A by a body consisting of all those xi's such that Wi is not epsilon. We can continue the derivation in the new grammar by a derivation from each xi that remains of the non-empty string Wi. We know this derivation in the new grammar exists by the inductive hypothesis. We also need to show part 2. If W is derived from A in the new grammar, then it is non-empty and also derived in the old. We're going to skip this part. So we're now ready for a new simplification of grammars, the elimination of unit productions. A unit production is one whose body is a single variable. We can eliminate all such productions. The idea is to discover, using a discovery-type algorithm, all pairs of variables A, B, such that A derives B by a sequence of unit productions. Eventually, a sequence of unit productions must end with the use of some other kind of production. So we can collapse the steps that use unit productions into the next one that does not use a unit production. That is, if B goes to alpha is a non-unit production and A derives alpha by unit productions, then we'll add A goes to alpha. Finally, we drop all unit productions. At this point, we do not need the unit productions and can drop them from the grammar. Here's the algorithm to discover the pairs of variables A, B, such that A derives B by unit productions. For the basis, surely A derives A by unit productions only. This is a sequence of 0 steps. For the induction, suppose we already discovered that A derives B by unit productions. Then if B goes to C as a unit production, we may add the pair AC. There are 2 proofs that we need, but we're not going to do them here. First, an induction on the number of rounds of the discovery process lets us show that the pairs we find are valid. That is, they really are pairs AB such that A derives B by unit productions. And conversely, we can show by an induction on the number of steps of a derivation from A to B, using unit productions, that we will in fact discover the pair AB. Another proof that we're going to skip is the proof that a new grammar has the same language as the old. Again, we have to prove something more general, that A derives W in the new grammar if and only if it does so in the old grammar. Each production of the new grammar simulates one or more steps of a derivation of the old grammar. That is, some number of unit productions, perhaps 0, followed by a non-unit production. Conversely, every use of a production in the new grammar can be replaced by 0 or more unit productions followed by a non-unit production in the old grammar. We can now combine the 3 simplifications to make a strong statement about grammars. If L is a context-free language, then L minus epsilon has a grammar with no useless symbols, no epsilon productions, and no unit productions. Another way to put it is that L minus epsilon has a grammar in which every production body is either a single terminal or has length at least 2. We apply the constructions just learned, but we have to be careful about the order. We must start by eliminating epsilon productions. We have to do this step first because eliminating epsilon productions can produce unit productions that weren't there before, and as we saw in an example, it can create useless symbols that were not useless before. That could only occur if the production was only used to derive the empty string, however. Second, eliminate the unit productions. Third, eliminate variables that derive no terminal strings. We explained earlier why this step must precede the next step in our quest to eliminate all useless symbols. So finally, we do the fourth step of eliminating all the unreachable symbols. We've almost got our grammars into Chomsky normal form, or CNF. Such a grammar has only 2 kinds of production bodies, single terminals or 2 variables. We're now going to give the construction of a CNF grammar for L minus epsilon, where L is any context-free grammar. Incidentally, one important use of putting grammars in CNF is that it gives us a relatively efficient algorithm for testing membership of a string in a context-free language. One might imagine that it was easy to make such a test by looking at all derivations of a certain limited length, but with epsilon productions and unit productions in the grammar, it is not obvious how long the derivation of even a short string of terminals has to be. Moreover, even if we could bound the length of the derivation, as we can, we'd still be faced with an algorithm that took an amount of time that is exponential in the length of the terminal string. Rather, by putting the grammar in CNF, we can make this test in at most the cube of the length of the string. Our first step is to do the cleaning we just described. The result is the grammar no longer generates the empty string, even if the old one did, but otherwise the languages are the same. But all productions bodies are either a single terminal or have length at least 2. Our second step is to turn those bodies that are not a single terminal into bodies of all variables. The trick is simple. For each terminal little a, create a new variable that we'll call a sub a. It's that. The job of this variable is just to generate the terminal little a, so replace a in all bodies of length 2 or more by a sub a, and add the production a sub a goes to a. That is, of course, that. Here's an example involving the production a goes to b little c b little e. C and e are terminals, so we must have created variables a sub c and a sub e with their productions. A sub c goes to c and a sub e goes to e. Then we can replace a goes to b c d e by a goes to b a sub c d a sub e. Now all production bodies that are not a single terminal are strings of 2 or more variables. If exactly 2, that's great because that's what CNF requires. But if a body consists of 3 or more terminals, we have to break the body into pieces by using new variables that appear nowhere else. An example should make the idea clear. If we have a production a goes to b, c, d, e, then we need 2 new variables, say f and g, and they are used only for this production. They may not appear in the new grammar except as we describe here. In general, if the body consists of n variables, we need n minus 2 new variables. The job of the first new variable, f, is to generate the whole body, except for the first symbol, b in this case. That is, we replace this a production by a goes to bf. Now f needs to derive CDE, that's the rest of the body. But that's too long, so we use G to help. G derives only DE, that's this production, using the production G goes to DE, and the production for F becomes F goes to CG. Thus we've replaced A goes to BCDE by the 3 productions that meet the CNF requirement. A goes to BF, F goes to CG, and G goes to DE. These three productions can simulate the effect of the original production, although they take 3 steps to do so. Thus, making this change surely allows the new grammar to generate anything the old one did. But the new grammar doesn't generate anything the old one didn't, so the languages are the same. The reason is that once we choose to replace A by BF, we are forced to replace F by CG and then G by DE because these two variables have only one production. Thus, using A goes to BF in the new grammar is tantamount to using A goes to BCDE in the old. We thus have an argument why the transformations from clean grammars to CNF grammars do not change the language. You can do formal inductions on the length of derivations in these grammars, but I hope these less formal arguments are convincing. Today we're going to see an automaton that is the equivalent in power to the context-free grammar. The equivalence is analogous to the equivalence between regular expressions and automata, epsilon NFAs in particular. The automaton is called a pushdown automaton, or PDA, a term that was in use long before there were personal digital assistants. After describing the mechanics of the PDA, we'll talk about 2 different but equivalent ways that PDAs can define a language. We'll also mention the deterministic PDA, since the standard model of the PDA is the non-deterministic version, with epsilon transitions allowed. One of the key points to remember is that PDAs define all and only the context-free languages. But unlike finite automata, the non-deterministic version is strictly more powerful than the deterministic version, and only the non-deterministic version defines the class of context-free languages. However, the deterministic version is quite important in compiling, since parsers for programming languages usually behave like a deterministic PDA. Most programming languages are designed to be recognized by a deterministic PDA. For example, we mentioned previously the class of LL of 1 grammars, and such a grammar can be converted easily to a deterministic PDA. We'll get to a formal definition of a PDA shortly, but to start, think of the PDA as an epsilon NFA with an additional stack on which you can store symbols. Like any stack, you can only see the top symbol. The next move of the PDA is a function of 3 things. The move can depend on the state it is in, just like a finite automaton. The move also depends on the next input symbol, or the PDA may make a move on epsilon, that is, without regard to the next input symbol. This behavior is exactly like that of the epsilon NFA. But the thing that makes the PDA different from the finite automaton is that it has a stack of symbols chosen from a finite alphabet, and it can use the top symbol to help decide on the next move to make. Here is the image of a PDA we should keep in mind. At the center is the state. Like the state of the finite automaton, it controls what happens. There is some input which is waiting to be processed by the PDA. The PDA can only see the next input symbol and can use the symbol to help decide the next move. It also has the option to make the move on epsilon without consulting the input. And it has a stack of symbols. It can see only the top symbol and use that to help choose the next move. Moves of the PDA can involve a change of state, like the finite automaton, but it can also push or pop the stack. In any situation, that is, in some state with some next input symbol and some top of stack, the PDA has a finite number of choices of next move. Since it is non-deterministic, it is perfectly acceptable for there to be more than one choice. A move choice consists of a change in state, which could, of course, be to the same state it is in, a manipulation of the stack. At each move, the top stack symbol is replaced by a string of stack symbols. If the string is empty, it has the effect of popping the stack. If the string is of length 1, then the top stack symbol can be changed, or not, since the replacing symbol can be the same as the original. If the replacing string has length k greater than 1, we can see the move as a change of the top stack symbol, followed by k-1 pushes of symbols. Now we'll give the formal notation and usual symbols for the components of a PDA. There is a finite set of states for which we tend to use Q, just as for finite automata. There's a finite input alphabet for which we'll continue to use sigma. There's a finite stack alphabet, the symbols that can appear on the stack. For this alphabet we use gamma. There's a transition function delta to be described shortly. There is a start state, typically Q0 as for finite automata. There's a start symbol. This symbol is a member of the stack alphabet, and initially the stack contains only this symbol. And there is a set F of final states, again analogous to the finite automata. There are conventions for PDAs that are analogous to the conventions we made for automata and grammars previously. We continue to use lowercase letters at the beginning of the alphabet for input symbols. However, for PDAs, it is sometimes convenient to allow these letters to stand for epsilon as well as the symbols of the input alphabet. Capital letters at the end of the alphabet are stack symbols. Lowercase letters at the end of the alphabet are strings of input symbols. Greek letters at the beginning of the Greek alphabet are strings of stack symbols. We always write stack strings so the top of stack is at the left end. The transition function for a PDA has three arguments. The third argument is the symbol at the top of the stack. First comes a state, as for finite automata. Second, an input symbol or epsilon, as for the epsilon NFA's transition function. And last, a stack symbol. Delta for state Q, input A, which can be epsilon, and stack symbol Z, is a set of 0 or more actions. Each action consists of a next state P and a string alpha of stack symbols, possibly empty, with which to replace the top symbol Z. To summarize, when delta of Q, A, and Z contains P alpha, then one choice of move for the PDA when it is in state Q sees A at the front of the remaining input and has Z on top of stack is to go to state P, remove A from the front of the input. Of course, if A is epsilon, then the remaining input doesn't change, and replace Z by alpha on top of the stack. Note that although the PDA may have choices, several different P alpha pairs, it has to pick one pair and then do both things associated with that pair. It can't pick a next state from one pair and a stack string from another. Let's design a PDA for our favorite context-free language, the set of strings with the form 0 to the n, 1 to the n. Okay. We need three states. Q will be the start state. It represents the condition that we've so far seen only zeros on the input. P is the state we go to when we see the first one. We use the state to remember not to accept a string if we ever see any more zeros. And F will be the final state. It's there only so we can accept when the number of ones matches the number of zeros. We also need two stack symbols. Z0 is the start symbol. It has an important job. It marks the bottom of the stack. As we read zeros on the input, we will push one X onto the stack for each zero we read. As ones come in, we pop one X for each one. So when the bottom marker, Z0, again becomes the top stack symbol, we know we have seen exactly as many ones as there were zeros, so we accept. Here's the transition function of our PDA. Initially, Z0 is at the top of the stack. When we see the first zero, we push an X onto the stack. Notice that the replacement string is XZ0. That's that. That string replaces Z0, but the net effect is that the Z0 remains and X is pushed onto the top. Remember that stack strings are written with the top at the left. We remain in state Q as long as zeros appear on the input. After the first zero, each additional zero causes the X on top of the stack to be replaced by two X's. Thus, the number of X's on the stack always equals the number of zeros read from the input. When a 1 appears at the front of the input, if X is on top of the stack, then we go to state P and pop the top X. Notice that there has to be an X on top of the stack, so if the first input is 1, When we still have Z0 on top of the stack, we have no move at all and can never accept. As long as more 1s appear on the input, we stay in state P and pop an X from the input. Thus, after seeing n zeros followed by m 1s, the number of x's remaining on the stack will be n minus m. And thus, after seeing n zeros followed by exactly n 1s, there are no more x's on the stack, and the top symbol becomes z0 again. The last move of this PDA says that if we are in state P with z0 on top of the stack, then without using any input, we go to state F. The z0 remains on the stack, although that is not important. Here's a moving picture of the PDA we designed with 0, 0, 0, 1, 1, 1 waiting on the input. Initially it is in state Q with just Z0 on the stack. That's the initial configuration. For the first move, we consume the first 0 from the input and replace Z0 by XZ0 on the stack. Notice the X is on top of the Z0. It's at the top of the stack. We consume another 0 and replace the top X by 2 X's. And the same thing happens again. Now the first 1 is consumed from the input. We transition to state P and pop the top X. Staying in state P, we consume another 1 and pop another X. Same thing. Now all the input is gone, but we have Z0 on top of the stack, so with epsilon input we can go to state F and accept. We're done, and we accepted the input string that was consumed, 0, 0, 0, 1, 1, 1. To talk more formally about the behavior of a PDA, we need the notion of an instantaneous description, or ID. The ID tells us the current state Q, the remaining input W, and the stack contents alpha. Again, remember that the top of the stack will be the leftmost symbol of alpha. There is an analogy between derivations for a grammar and sequences of IDs for a PDA. The IDs are analogous to the sentential forms of the grammar. In place of the double arrow, we use the turnstile symbol, that's this, to express the idea that one ID I can become another ID J by one move of the PDA. That is, suppose the first ID has state Q and input AW, where A is either the first symbol or epsilon, whatever is used for the next move, and it has stack X alpha, where X is the top symbol and alpha is then everything below that. Suppose the delta of QAX contains P beta. Okay. Then a possible next ID has state P, that's this. Okay. W is remaining on the input because A got consumed. Again, A may be a symbol or epsilon, doesn't matter. And with beta alpha on the stack, where the X here got replaced by the beta. We also have a goes to star relation for IDs defined analogously to the way we defined arrow star for sentential forms. That is, the basis representing 0 moves says that any ID goes to star itself. And for the induction, if I goes to J by some number of moves, possibly 0, and J goes to K by one move, then I goes to K by some number of moves. Here's the sequence of IDs that we get from our previous example. The input is 0, 0, 0, 1, 1, 1, so the initial ID has state Q, that input, and stack Z0. Here it is. The first move consumes a 0 from the input and pushes X onto the stack. So this 0 got consumed, that's what's left, and of course the Z0 is now on the stack. The second and third moves do the same. can see additional x's being pushed onto the stack. Okay. Next, because the next input is 1, the state becomes p and the 1 is removed from the input. Also an x is popped, okay, and that explains that ID. And 2 more moves pop the remaining x's. It's that and that. And then in the final ID, the state P has become F, and we accept. We can summarize the sequence by saying that the initial ID, this, goes to star the final ID, that. We can also say that any of these IDs goes to star itself and also to any of the IDs that follow in the sequence we just showed you. In order to understand better the idea of acceptance of an input by a PDA, we have to ask ourselves, what would happen if there were an extra 1 on the input? We'll take that up on the next slide. Okay. The sequence of IDs is the same, except that an extra 1 tags along at the end of each input string. The last move, where the state changes from P to F, is still legal because a PDA can use epsilon input even if there is input remaining. State F has no transitions, so the sequence cannot be extended and the last 1 can never be consumed. We conclude that 0, 0, 0 followed by 4 ones is not accepted because the input was not completely consumed even though we entered a final state in the middle of the process of consuming the input. Okay. The normal way to define the language of a PDA is by final state. That is, L of P, the language of a PDA P, is the set of strings W such that when P is started in its start state, with W on the input and the start symbol on the stack, that's this ID, there is a sequence of moves of P that leads to an ID with a final state, there we are, with W completely consumed, it's that, and anything on the stack, I don't care. However, there is another way to define the language of a PDA, and this approach turns out to be rather useful, especially when we show how to convert PDAs to grammars and vice versa. We can talk about the set of strings that make the PDA empty its stack. This language is conventionally called NFP for a PDA-P. The N stands for null stack, although we're not really going to use that term. Formally, this language is the set of strings W such that started in the usual ID with input W, that's of course this, P eventually reaches an ID in which it has consumed all of W and its stack is empty. Okay. We don't care about the state Q. It can be final or non-final, doesn't matter. Thus, every PDA defines 2 different languages in 2 different ways. However, the classes of languages defined by all the PDAs in these 2 ways are the same, and in fact are the context-free languages, as we shall see later. That is, if we have a PDA P that defines a language L by final state, then there's another different PDA P prime that defines the same language L, but does so by empty stack. P prime will presumably define a different language by final state, but that doesn't matter. The point is that every language defined by final state by some PDA is also defined by empty stack by some PDA. And conversely, if a language L is defined by some PDA P by empty stack, then L is also defined by some PDA P double prime by final state. Here's a rough idea of how we convert a PDA P accepting L by final state to P prime accepting L by empty stack. Basically, P prime will simulate P. That is, it does what P does with a few exceptions. If P prime finds that P is accepted by entering a final state, P prime empties its stack. Since P and P prime are in general non-deterministic, P prime can also guess that P will read more input. P prime will then not empty its stack in that sequence of moves, but rather will continue simulating P. But since p prime accepts whenever it empties its stack, and p might do that on inputs it doesn't want to accept, p prime needs a bottom of stack marker to prevent it from accidentally emptying its stack during the simulation of p. Thus, we'll give p prime all the states, symbols, and moves of p in order to do the simulation of p, plus a few other bells and whistles which we'll explain next. First, p prime has a new stack symbol x0. This is the start symbol of p prime, and it also has the job of guarding the stack bottom against accidental emptying. That is, if p empties its stack, p prime will find x0 on top of its stack and realize that p can make no move from this ID. Although being non-deterministic, it may have other ways to proceed. P prime thus does not empty its own stack. P has a new start state S and an erase state E. P prime has several additional transitions. This rule says that in its initial ID, it has only one choice. It must change to the start state of P and push Z0, P's start symbol, on top of its own start symbol X0, which remains to guard the stack. P prime is now ready and able to simulate P. Until P accepts, all the moves of P prime are the same as the moves of P, with the guard X0 sitting at the bottom of the stack unseen. And if P prime enters any final state F of P, then P prime has the option of entering the erase state E. It pops the current top of stack symbol, which might be X0 by the way. In that case, delta of F, epsilon, and X0 was previously undefined by P. Moreover, in the erase state E, P prime has only the choice to keep popping the stack and staying in state E. Eventually, P prime empties its stack and accepts. Now let's explain the construction in the opposite direction. That is, P accepts some language by empty stack, and we must design P double prime to accept the same language but by final state. P double prime also simulates P with a few bells and whistles. First, P double prime needs a bottom marker to detect that P has emptied its stack. If P double prime sees this marker at the top of the stack after its initial move, then it knows that P has emptied its stack, and so P double prime must accept by entering its own final state. P double prime has all the states, symbols, and transitions of P. In addition, P prime has a new start symbol X0 that also guards the stack bottom, just like it does for P prime. P double prime has a new start state S and a new final state F. From the initial ID, P double prime goes to the start state of P and pushes the start symbol of P onto its own stack. It is thus ready to simulate P. Once in the states of P, if P double prime ever sees the guard X0 at the top of the stack, it knows P is accepted. P double prime therefore goes to its own final state without reading any more input, and therefore accepts by final state the input that P accepted by empty stack. And a final word about the deterministic PDA. In order that there never be a choice of move, we certainly want the PDA to have at most one choice of move for any state Q, input symbol A, including epsilon, and stack symbol X. But we also have to rule out the possibility that there is a choice between using a real input symbol and making a move on epsilon. To be precise, for no Q in X, can both delta of QAX and delta of Q epsilon X be non-empty. Such a PDA can have only one sequence of IDs, starting from the initial ID with a given input string. We generally assume acceptance is by final state, since if you accept by emptying your stack, you cannot ever process any more input if you're deterministic. While we shall not expand on the matter, the class of languages accepted by deterministic PDAs contains all the regular languages, obvious since it can simulate a deterministic finite automaton by just ignoring its stack, but it does not include all the context-free languages.